Hello guys, this is the third lesson of our formal language and automata series. In this video, I shall discuss parse tree, ambiguous grammar, and other such interesting features. So let's begin. Let's begin with parse tree. Suppose there's a sentence, there's a language and there are production rules and the starting symbol. And suppose your sentence is this A, and D. You have to reach this from S is equal to B, C, D. And there are some production rules, and following them, you reach it. Well, in the previous video where I discussed how to reach to a sentence from production rules, I stated that there are more than one way to reach the sentence. This is the reason for making for the concept of parse tree. We know that there are more than one way to reach the sentence, so there may be a confusion. Um, um, For example, if this derivation is done in a different way, a person may get confused. So, for better understanding, what is done is a tree-like structure is made, a binary tree-like structure. Um, I think I should not say binary. Binary means two nodes. It's not two nodes. It can be n number of nodes, but more broadly, it's a tree-like structure. Let me show you how. The first line is S is equal to BCD. So in the graph, what's done is first S is written, and from S, three nodes branch out. They are B, C, and D. And then in the next step, it's written here, B is changed to small a and capital A. B, C, D becomes small a, capital A, C, D. So in the graph, we'll also branch this P into small a and capital A. Similarly, after this, A is branched to small a and small a. So this A becomes small a, and this line becomes small a, C, D. So this A, this branches into small a and another small a. After that, C splits into small a and capital D. We use this production rule here. So C splits into small a and capital D, and same with the graph. C splits into small a and capital D. So as you can see here, we follow um, this procedure, this rule of how we reached this string from the initial starting symbol. We follow this and we apply it on the graph. um, at each level, we replace the variable with the replacement string. I hope you remember what the replacement string is. We replace the variable with the replacement string. Um, then like B becomes small a and capital A, and C becomes small a and capital D, because it's written here. We use this at this stage, we used it, so we are writing this. Similarly, capital D becomes capital D. Capital D's replacement string is small a, so it's the last step, and we replace it here. Capital D becomes small a. There's no way of making a mistake in this manner if we follow this step. Uh, in the past, it's very difficult to make a mistake, and it's graphically written here, so it's easier to understand and follow. And if you can see this curved arrow-like structure, you was probably wondering what it's all about. But if you observe carefully the leaf nodes of this parse tree. If you follow this arrow from left to right, it's going like this, here to here to here to here to here to here, and up till it reaches here. So if you connect the leaf nodes one after the other from the left to right, you observe that we get small a, small a, small a, small a, small a, and small d, small a, small a, small a, small a, small a, and small d, five small a's and one small d. This was our string, and in this way we reach the string. We derive the string from the parse tree, from the tree actually. So the parse tree is also known as a derivation tree. This method of this thing of reducing the variables at each step is known as derivation. We're deriving the sentence from the starting symbol. So this is a derivation, and this is the derivation tree, because in this tree we are deriving it. At each stage we are breaking the variable into its constituting variables, just like we did in the derivation here. An important thing which I should state is, before you go on to this parse tree, it's very important to first compute this derivation. After computing this derivation, it becomes really easy to make this parse tree. And in your examination, I suppose it will be compulsory to draw this to figure out this derivation first, to write it down first before proceeding to the parse tree. This is the concept of parse tree. It's pretty simple. Now let's move on. This is an example. Suppose our starting symbol is small a, capital S, C, D, or B. I hope you remember this pipe symbol means or, and C is small b, capital C, capital D, or E, and D is small d, capital D, or DD. And this is our replacement, sorry, this is our string which we must derive. Well, starting, okay, this is first our reference. We must write this actually and in a proper way. I've written this for written this quite quickly, and I missed a few details. As you can see, it's not absolutely perfect, but you must do it perfectly. Well, at each step I showed how I replace S is first broken down into small a, capital S, C, D. S is replaced with B, and C with E, D with D, D, and C with D, and so on. In this way we reached the string from the starting symbol. Same thing here in the graph. S is broken down into all its components, A, S, C, D. Then there's nothing to break here. Then S is again broken here into its components, and C with E, D with D, capital D, then capital D with D, D, S with B, C with E, D with small d. As you can see here, it's more pleasant to see this tree-like structure instead of all this gibberish writing. So parse tree is actually much more useful. And this arrow, as you can see here, it following this arrow we can reach our string which we must obtain. Well, an important property of this parse tree which I must state is, the leaf nodes will not be a variable, and the intermediate nodes may be a variable, may be a terminal, but the leaf nodes will always be a terminal. This is pretty obvious actually, but still I think I thought I should say, that's why I said. Now let's move into ambiguous grammar. Now what is ambiguous grammar? Well, in English language, suppose a sentence, or rather a thought can be expressed in more than one way. This at times causes confusion. That's because there are more than one way of representing an idea. Same thing with other grammars as well. As we are dealing with grammar, so we have this problem as well. And it's technically termed ambiguous grammar. Now the definition is a terminal string W is ambiguous if there exists two, two or more parsed trees for W. Before reading the second line, let's first take an example. Example, suppose S is S plus S, or S into S, or A or B, and our string is A plus A into B. And there are actually two ways of reaching this string. First way is we break down S into S plus S, and then S is replaced with A. As you can see, S is also A here. S is replaced with A, and this other S is replaced with S star S, S star S, and this is S is replaced with A, and this S is replaced with B. Following this line, following the leaf nodes, we reach A plus S, I'm sorry, A plus A star B. Now moving on to the other graph here, we split S into S star S. Earlier example we split into S plus S, we split into S star S, and then this S is broken into S plus S, and this is S is replaced with A, then this is with A, then this is with B. So we get A plus A star B. So there are two ways of reaching this sentence, and this is actually a problem. This is known as ambiguous grammar. Now let us reread the definition. Terminal string W is ambiguous if there exists two or more parsed trees for W, means two or more ways of deriving the string W. And in this case, in this example, it's true, there are two parsed trees, so this is an ambiguous grammar. Now let's move into second sentence. A context-free grammar is ambiguous if there exists some string in the language having the grammar G which is ambiguous. If at least one string, at least one string is ambiguous in a grammar, then the entire grammar is known as ambiguous grammar. If at least one string is ambiguous, then the entire grammar is known as ambiguous grammar. This is pretty easy actually, it's not very complicated. To in a simplified form, in a nutshell, if there are two pass trees for a string W, means even speaking simply, if there are if you can derive the sentence in two different ways, two or more different ways, then it's an ambiguous sentence, as simple as that. Let's move on. What is this? Okay, useful and useless variable. Well, we have not come across an example as of yet where a certain variable is not used at all. If in the grammar, if in the grammar the variable is not used at all for any string, the variable is not used for making any string whatsoever, then that variable is known as useless variable because it's not used at all. Let's read the definition once. If some variable cannot be reduced to terminals or is not used at all in any string W, it's called useless grammar. The first part, if some variable cannot be reduced to terminals. Well, a variable has to reduce to terminals. Otherwise it cannot be used in a sentence. A sentence has only terminals and no variables. So if a variable cannot be reduced to terminals, it cannot be used in a sentence. So this is what the first part says. Second part says it's not used at all. So yeah, it's not used, then it's useless. How to remove the useless variables? Let's read this first, and we shall move to an example and you shall understand better. Okay, remove the variables from the production rule that cannot be reduced to terminals. Remove the variables from production rule that cannot be reduced to terminals. Those variables which cannot be reduced to terminals, that is the first part of this sentence. Remove them from the production rule and rewrite the production rule removing them. Now draw the dependency graph. I shall show you how to draw the dependency graph, and then find all variables those cannot be reached from the starting symbol. I shall show this. Okay, take this example. S is BC, then B is small a capital B or AA, C is DD, D C is A or AC. Now if you observe carefully, E is small a and capital F. Now there is no F mentioned here. So this cannot be used. F is unknown. That's why AF is useless. That's why E equal to AF has to be removed. After removing, the production rules becomes S is BC, B is AB or AA, C is DD, DC is AC. Then we must draw the dependency graph. Well, to draw it, draw draw all the variables from the new production rule. From this, draw all the variables. Now draw the connection. For example, from S we can reach B, we can reach C. So from S an arrow will go to B, an arrow will go to C, arrow to B, an arrow to C, and from B we can reach AB, small a capital. So from B we can reach B. So B has a self loop. Then C can reach small d and capital D. Okay, so sorry, C can reach only small d's, so there will be no arrow from C. Then D reaches to C, so there will be an arrow from D to C, and finally E reaches to C, so there will be an arrow from E to C. But if you observe this graph carefully, now we can understand. Now let's read the third point. Find all variables that cannot be reached on the starting symbol. Remove those variables from the production rule. Now, which variable cannot be reached from the starting symbol? In our case, the starting symbol is S. We can reach B from S. We can reach C from S. Can we reach D from S? No, we can't. We can't reach D from S. This arrow goes from D to C, but from C to D, no arrow. We can't reach. Can we reach E from S? Is there any way? No, there is not. There is no way to reach E from S. So these two variables has to be removed from the production rule. So the minimized dependency graph becomes S to C, S to B, and B as a self loop. The minimized production rule or reduced production set is S is BC, B is AB or AA, and C is DT. So this is how you remove the useless variables from the grammar. Now let's move into an example. This is an important example. Suppose there's this production rules. S is BC, B is small a capital B, and C is small c capital C or D. Now if you observe carefully, B is small a capital B. So we can never reach a set of terminals from this B. If we follow B, we can never reach a set of terminals because B is small a capital B. Then if we reduce B again, it will be again small a capital B. It will go on forever. So this has to be removed. We can reach the terminals from this. Has to be removed. So what's remaining? This and this. Now let's draw the graph. We draw S, we draw C. Now let's draw the dependency. uh, okay, I'm sorry, I made a mistake here. um from S to B, this C won't be here actually. This C won't be here. I'm so sorry, this C won't be here. So considering this C is not here, from S to B there is a connection, but B is not here, so there will be no connection from S to C or from C to S, because has a self loop here, but no connection with each other. I'm sorry, S is only pointing to B, not to C. I made a mistake here. Then all productions are useless, so production rule is 5 or empty, and this is a usage, an example of useless grammar. So this is all for this video. In this video we learned parse tree, ambiguous grammar, useless grammar, and how to remove the useless variables. If you like this video, do it like and do share with your friends. Thank you. And in the next tutorials I shall discuss some other concepts of this chapter. Thank you.